All right, gang, we're rounding third base. We're almost home with this universe and galaxy stuff. We're going to be filling in 29 through 31 on your guided notes today. And the first blank to fill in drives this point home. Think about the last lesson that you watched. We looked at the Hertzsprung-Russell diagram or the HR diagram. And if we would have been in class, we would have done a station lab. You know, where we move all around the room and you've got watch it and research it and all that kind of thing and organize it. We would have done an HR diagram station lab. So to really drive this point home, but we don't have time to do that. And trying to set it all up in EDSB is kind of crazy and a nightmare, and then we run out of time. So anyway, we'll just do it this way. But the main point, big takeaway from the HR diagram is that the hot, brighter stars that are out there in the night sky are actually blue in appearance, and you can see these at night. Last night was a great night to watch stars, to go out if you can get away from city lights, and obviously you can tell the red ones. It's kind of like where you look up there and you're like, it kind of looks a little bit red, but I'm not quite sure, and if I stare at it a little bit longer, it seems like it's red. Same way with blue. You look at some of them and you're like, yeah, I think that's kind of blue, but I'm not really sure. It just looks like a white dot. It's that. You look at it with certain instrumentation and you can tell the difference. So hot, bright stars tend to be blue in color, and the cooler, by comparison, cooler dim stars are red in color. Now, related to the light that comes from stars, we got two terms that we use. The best way that I could describe this would be like if you're going down a country road and somebody approaches you and they obviously have their high beams on. Now, far enough away, you can tell that they have their high beams on. But the closer that they get to you, the more irritating it is to your eyes, because you are encountering the absolute magnitude. When you can see them from really far away and tell that their high beams are on, because of the type of light and the amount of light coming at you, that's the apparent magnitude. You sit there and you go, well, apparently they have their high beams on because there's so much light. But then when they get up close, you're like, dude, knock them off. Okay. Apparent magnitude is how bright a star appears from Earth or even on Earth. Either one of those words would be fine. How bright the star appears from Earth. And you can tell that, again, stepping outside into our living laboratory and looking at stars, you know, in the sky, because some of them seem really bright and some of them seem, you know, they're there. Yeah, I can tell. That's you are perceiving the apparent magnitude. So how do you get the absolute magnitude? You would have to get up right up next to that star and measure the luminosity, the lumens, L-U-M-E-N-S. Lumens is a measure of light. And when you're buying light bulbs, we're used to purchasing light bulbs based on how many watts they are. Well, that's wrong. I mean, we really shouldn't do that. If we're trying to buy a light bulb for what effect it has in the room, we buy a light bulb because it emits light. So what you're really looking for on that package is the number of lumens, L-U-M-E-N-S. And that's the unit that they're measuring when they measure brightness. Okay? So, number 30, apparent magnitude is the brightness of a star as it appears from Earth, but absolute magnitude is the true brightness of that star. Last subject we're going to do today real quick, or at least in this lesson, is black body radiators. Here's the example. I used to have a black car. It was a Mazda 626. And that is a car that if it was sitting outside all day long in the sunshine, I would not want to put my hand on it, because things that are black, as you know, tend to absorb everything. They absorb all the EM radiation from the sun, right? They absorb everything. The problem with things that are black is that they don't emit anything except heat. Think about that black car sitting outside, maybe in a parking lot, and, you know, it's July, and you come up and accidentally put your arm on it. Oh, you could fry eggs with that thing, right? Because it's absorbing every frequency of the EM spectrum. And what's it emitting? Light. Well, there's things out there in space like that, and we call them black body radiators. They're theoretical, really. And the idea there is it's the same thing. It absorbs all radiation, but it emits heat. Okay? And so the closest example that we would have to that would be our sun, our star. It does absorb radiation, but it also emits some light, right? It emits some color. Sure it does. But the main thing that it emits is heat. Sure does. Okay, so the idea of the black body radiator is that they absorb all energy, but they radiate heat. Okay? Again, there's a video link right there if you want to copy that and paste it and look about black holes. It's kind of cool. It's not anything we're filling in our blanks, but it's just kind of there for fun. Okay? And that covers everything we wanted to deal with in this one. And remember, we're trying to finish all this week, or through the weekend. And if you need a couple of days through next week, relax. It'll show up in Edsby that it's late. I'm not taking any points off. Again, I'd rather you guys get it done completely and turn it in so that you submit it once, I grade it once, and we're rolling. All right? And we'll see you on the next one.